So everyone ready? Want to go? Food coma? No? Okay, I'll try to entertain you a little bit. I won't do a dance though, okay? All right, next 90 minutes, we're going to talk about multi-site for VXLAN EVPN. Try to guide you through the architecture and the technology of it. I hope it's going to be interesting. 395 slides? No, it's less. It's much less. This is not a TV show here. My name is Lucas Kradiger. I'm working in data center for, I think, 12 plus years within Cisco and did some stuff outside before, so I know how hard it is to sometimes consume technology. So I'll try to explain how it works instead of just showing you a CLI, what you need to enter to get a result. So I'll try to walk you through how things work, how things are intended to work, and sometimes how they don't work. For the session, we have these Teams rooms, WebEx Teams rooms, where you can go and subscribe, you can ask questions. Helps me after the show to still talk and chat to all of you, so feel free to sign up. Most often, we also post certain files or PowerPoints or other things in there. If you're looking for the PowerPoint, it's in the event app. On the very bottom, you can click on it. It's the same PowerPoint I'm going to present here, is shared there, and this is the agenda for the next 90 minutes or so. Introduction is one slide. It's about what the session is about, and then we immediately go into what is multi-site use cases and give a deeper look, as well as some packet forwarding details on this whole multi-site story. As said, introduction, I want to keep it brief. Well, look at this. I use brief as the second word, so I want to keep it brief. I want to explain you first what you thought around what are we doing from a standards perspective when there is VXLAN as an IETF working group standard or working group draft, RFC, and on the other side we have BGP and EVPN being in there. So I want to give you a little bit of insights, what's their standard track versus informational track, and what we're doing around that with multi-site. Then what is multi-site about? What have we thought about when we came up with this multi-site? I mean, I guess you probably heard of it, so that's why you're here, and thanks, obviously, that you joined me here this afternoon. There we go, use case and deployment scenarios. There's so many, I'll try to put a couple of groups in there, and then border gateway discussion or BGW discussion is definitely part of the essence, and what you're seeing of how updates work in BGP, how you install things, how you advertise things, or how you just forward the packets and re-encapsulate in these ominous border gateways, which we obviously have as the core functionality of that infrastructure. So what is multi-site? Has anyone heard of Inter-AS option B? Okay, there's some, okay. Has anyone heard of external BGP? Yes, of course. Thank you, you make me easy. So in BGP, there's something called the next hop behavior. If the neighbor is an external BGP, what you're doing, you're changing the next hop to that neighbor. When you do that with tunnels, that's not the behavior you're looking for. When you do that actually with tunnels, you want that the tunnel goes from the ingress point to the egress point. So from the source VTEP to the destination VTEP. If there is a node in the middle which has its own AS, what happens? We're not pointing to the final exit, we point to somebody in between, and that somebody in between doesn't know how to react. So you need to define that next hop behavior in tunnel modes, or in EVPN, in this case, Ethernet VPN, which we're talking about. And that's basically what the session is going to be about. Well, it's a little bit more than just that, but the essence lies in how BGP behavior is for tunnel infrastructure. Now, it's not just BGP. It actually goes a little bit further into address family in BGP, which is called EVPN. And in EVPN, or Ethernet VPN, there are functionalities how we can build these overlay tunnel systems driven by the control plane. If you want to have multiple of these tunnel systems, what we often call fabrics, or leaf spine networks, or whatever else you want to call them, when you have multiple of them, you want to interconnect them. And in order to define how the procedure is, somebody needs to write down what is that way of going. And this is when, for EVPN, RFC 9014 started. RFC 9014 had another name before. Internal working group name was DCI overlay. Fancy terms, doesn't matter. But the essence of this is, how can I interconnect multiple data center networks of EVPN and use EVPN in between to do that stitching? Doesn't matter what data plane, just matters that you're using EVPN left and EVPN right. Now, 9014 defined a couple of methods in there. And all of these methods were predominantly, actually not predominantly, were exclusively on how to interconnect two networks with layer 2. How magic is that? An Ethernet cable in between and we're done. Yes? No? It is, right? Now, EVPN is a little bit smarter than just having Ethernet, or what we call flood and learn in that case, and MAC addresses. There's also a combination of MAC and IP addresses. So we're feeding more than just a MAC table as a result of it, so we need to define a little bit more than that. And very specifically, even if we use an Ethernet cable between two of these networks, we need to define what are we doing with the IP portion of it. How are we doing the marrying of the MAC and the IP address and create, again, that coherent update information, which we often refer to as EVPN route type 2. How are we doing this? So in 9014, we created two gateway modes. One is what we call the decoupled gateway, section 3 in there. The other one is the integrated gateway. The decoupled one, look how magic it is. We have VXLAN EVPN network. We terminate it. We take an Ethernet cable. We have a DCI router. We do another EVPN fabric, terminate at the remote sites, WAN edge or DCI gateway, put another Ethernet cable, and bring it into the other fabric. Great. Why do we need to define that? Again, I mentioned briefly, there is more than just MAC addresses in EVPN. Great to do that, great to define that, but the real magic sits actually if we can do something what we call often tunnel stitching. So I can use a VXLAN EVPN fabric, I put a gateway in front, I recreate the tunnel to the other side, terminate the tunnel, recreate the tunnel into the last fabric where we again have tunnels. That's the integrated gateway mode, and RFC 9014 defines these two tunnel modes, or these two interconnection modes, the decoupled and integrated gateway, for layer 2 networks. What are we missing? What's about layer 3? Bridging is great, routing is better. So what could we do? Create another address family, there's one, called L3 VPN, VPN v4, VPN v6, and create another BGP session, parallel to this. Why should we do that? We have a protocol or a address family of EVPN that is able to do MAC and IP information binding in a single control plane message. Why should we add additional address families? Why should we do more BGP sessions? Why should we even ask for more tunnels? And that actually is when we started saying we need to do more than just defining the layer 2 procedure. We need to look at the whole story a little bit more holistically, and we started writing what we call multi-site, or the multi-site EVPN draft. If you go to that draft and you read it, I hope it's still up to date. We have to do it every 6 months, so the version number goes up and doesn't expire. But when we wrote and when we started doing this, every layer 2 procedure is based on RFC 9014. Great. So it's congruent with it, not competing with it. But we did a little bit more than just doing and adding whatever is already defined somewhere else. We wanted to make sure that we also address the gaps. By the way, if you have insomnia, these are perfect documents to read if you really, really, really want to sleep. It helps. Even writing them, my eyes are closing. Okay, okay, next one. So again, we wrote this. It has a best notation. It's shipping for, 7 years or so. what we have described in there. We're working on the adoption and then subsequently creating that informational draft to be out there. So it's there. We're basing on a standard. We're just extending the notations in there. Now, given that I already said there was something missing, that we even came up with this document, with this draft there, was the obviously layer 3 part. So we wanted to use not just layer 2 extensions, but also layer 3 extensions. And we also wanted to do not only unicast, we also want to make sure that the multicast part goes there. Makes sense, I guess. Anyone runs data center which are L3 only? Anyone using data centers with L2 only? You see, it makes kind of sense that you want to have both when you're doing that step and going into an overlay fabric like this. So we tried to define the solution of how you do an interconnect of layer 2 and layer 3 with EVPN, unicast, multicast over a VXLAN tunnel. And that is another piece which is a main difference from RFC 9014. 9014 has every possible encapsulation you could think of. MPLS, PBB, and so on and so forth. We said, okay, we're bringing it down. We want to make a more integrated approach to how the fabric is. Let's make the DCI an extension of the fabric itself by using the same control and data plane methods within the fabric as well as between the fabrics. So it's VXLAN focused. Now, I could just tell you what it is about, or I can let you read what it is about. And as a good citizen I am, I try to do comparison. If you go and read one draft and you read the other draft, have you ever tried to compare them? Diff tools are great, but the language is so different. You have to uncover so many different details. So I'll put these tables next to each other. RFC 914 is the further left part, and then the multi-site differences on the right. You see 9014, or the DCI EVPN overlay one, has two gateway modes, integrated and decoupled. Why do I need to discuss the decoupled? I want to have the integrated one, so I'll only focus on the integrated one. All the different encapsulation, well, I focus on what we try to build it integrated to the DC fabric, which is VXLAN. Let me just ask the VXLAN one there. Can we do decoupled or other encapsulations with multi-site too? Yes, absolutely we can. We just haven't described it. It's just a matter of going to these procedures. Now, as we looked at the mostly and very dominant MPLS-related descriptions in EVPN, we found a couple of suboptimal arrangements which are there. One of it is, in MPLS you use labels, and labels are doing multiple things. It defines a forwarding characteristic as well as the tenancy characteristics. In VXLAN, the forwarding characteristics is IP, and the tenancy characteristics is VNI. You heard of these different little things? So I cannot use a VNI to say forward to that VNI. I have to say go to that IP, and when you reach that IP, use these VNI for the tenancy. So I have a less stringent combination I have to adhere versus in MPLS where I can just stack labels in there. So we looked at this, and ECMP, or EcoCast multipath and IP address, is something very costly. Whenever you do ECMP changes, somebody has to calculate. So how can we avoid that, and how can we avoid to using all of these many resources in ECMP? And we said, let's do that Anycast thing. It sounds cool. So what is Anycast? Anycast means that multiple devices have a same representation, a same IP address, a virtual IP address. So we created a mode in our multi-site solution, which is basically has 2, 4, or 6 devices, individual devices, having all the same IP address, the same virtual IP. So guess what happens in convergence cases? Guess what happens in changes in the network? Nothing. Because if one goes away, there's still N remaining with the same IP address. So from a network perspective, there's no change. When I do an ECMP change, meaning I have 6 devices, one goes away, I have to actively go and, in the remote location, do a recalculation that guy doesn't exist there anymore. And for that amount of time, that's what we call a reconvergence event. So that's why we did a VIP address approach or an Anycast approach by Having that as the default mode, we still allow to do that multi-path approach or that overlay ECMP approach, which is perfectly fine in either way. Scale and convergence was one of our main focus, which we want to improve. The other thing which we felt is necessary to address is the layer 3 part. EVPN has a route type for IP prefix routing, or an equivalent to layer 3 VPNs. It's called the route type 5. It's an IP prefix route. So we wanted to add IP routing to that whole story. When we add IP routing to that whole story, we're not anymore 100% congruent with what RFC 9014 does, because it only does layer 2. So we added the route type 5 procedure, as you see, I don't have a clicker, as you see over there, to this whole solution. So instead of asking you to implement a different procedure or a different RFC, which we, again, based on, because we also wrote that, we just integrated the same procedure into that multi-site bucket and called it QUIP. Does that help to understand why there are different documents which are actually writing exactly the same thing, and Cisco does its own thing? No, we didn't do our own thing. We just documented on what we're doing by combining two different RFC. And this is exactly what it is in a nutshell. We had missing pieces we were looking for. We listed them. We complemented them. We wrote them in another document. That's what you got. That's what multi-site is. Does that help from an understanding perspective? So that's the history. That's the dry part. Now we can go to the real fun stuff. That was the dry part. OK, everything else will be dry too, but sorry for that. So that's why we built multi-site. That's the only reason why we built multi-site. There was a void. How do you close a void? You listen to customers, all of you, and then fix it. Do it. Multi-site has multiple functional components and use cases. So use cases is what we came off, what we think makes sense. And when we started with multi-site, what could have been our first use case we think of? Everyone would say DCI, data center interconnect. Well, actually, we didn't. We had another problem to solve at that point. In the world when tunnels started, everyone wanted to build big fabrics, big tunnel fabrics, everything end to end. Which means if you try to upgrade a switch in a network with 500s or thousands of switches, how many people do you need to call to get a maintenance window? Yes, on Christmas at 3 a.m. in the morning for 30 seconds. We looked at how can we do it different, and we came up with, let's do the idea of compartmentalize infrastructure, meaning build smaller fabrics, but allow these smaller fabrics to interconnect at layer 2 and layer 3 consistently. So in the same data center, instead of building that huge block, you build a smaller block, you build another smaller block, you build another smaller block, so you scale as you grow, and you interconnect them. Now, as you interconnect them, you get control. So these Bs there, these border gateways, allow me to control what I actually need to extend between left and right. Not just from a VRF or IP forwarding or a bridging perspective, VRF or layer 2 network perspective, but also from what kind of traffic do I want to forward. You all probably heard of BUM, broadcast, unknown unicast, and multicast, and at these border gateways, at these integration points, I can actually control broadcast, unknown unicast, and multicast with rates. So a loop in one network doesn't have to bleed over to the other network and bring everything down. That was our first thought, to have a better hierarchical model for the overlay. Because you're building beautiful topologies with your routers and the links in between, leaf, spine, super spine, up, down, left, right, interconnect. But then you put a tunnel on the top and do that tunnel end to end, which means you flatten down that whole hierarchy. There were a couple of other issues there, which is related on how we do replications. And specifically when it goes to that BUM replication or broadcast unknown unicast multicast replication, or just how would be a broadcast replicated from A to B. In tunnel networks, as you see here on the left, you often have an ingress replication approach where one node, the one on the very left here, has to multiply a broadcast for every remote tap that exists. So we have here leaf 1, the very left one has to leaf 2, leaf 3 has to go over that superspine model to 1, 2, 3, 4, 5, 6. So how many copies do I have to do? I have to replicate 5 packets. So that means bandwidth of 1 becomes bandwidth of 5. Does that make sense? Is that okay? You guys are following? Now, can I do a hierarchical model for that too? And the answer is yes. So by having that local function there, that border gateway, which keeps that tunnel system local, I say, okay, I replicate to my leaf 2, my leaf 3, which are local to me, and I say, if there is somebody interested on the remote side, I'll send it to the border gateway. So how many replications do? I do 3 instead of 5. Do you only have 5 VTAPs or 6 VTAPs? You probably have 10, 20, or 30, even 50 or hundreds of them, so the multiplication becomes even more stringent if everything is on the ingress node or on the first node. If I do the replication breakdown or I do that hierarchically, then I can offload it to the closest node that actually needs to do the fan out, means the one that has to replicate to the direct neighbors. In this case, the border gateway on the remote fabric or on the remote side will do the multiplication instead of the ingress node does it. It's a little add-on you get, so optimize your bandwidth in this. Another piece was scale. As I said, everyone wanted to build these humongous big tunnel fabrics. I was one too. I want to have a VTAP on every server. I'm not there. Anyway, so we want to have big tunnel systems and say, everything flat, everything from ingress to egress, I don't have much control. It bleeds, right? It becomes a tunnel proliferation. It becomes madness, if you want so, a spaghetti plate. That was a reference to my Italian friend, by the way. So we thought about how can we scale, or how can we build scale better. Said, okay, 256 VTAPs everyone can do. Easy peasy. Let's do that. But let's multiply that. Let's multiply the beginning. We did 12. Then we went 25. Today we're at 128. So you literally can do 128 fabrics of 256 leaves. Who is good in math? 32,768 VTAPs, meaning tunnel endpoint, can have a layer 2 segment stretched or a layer 3 segment VRF stretched if you want so. Is that big enough? When I'm looking at some hardware tables which are limited to 1K, 2K, or 8K, this is a multitude of that. And it is not just wild, it is actually going in a controlled fashion, given at the border gateway level where the multi-site domains are separated, you have control of what you want to extend. So you don't even need to extend layer 2 everywhere you want or layer 3 everywhere you want. You have a control point of how far you want to go or how far you need to go in these cases. Very often it doesn't really click, but I'll give you a little bit of insights how tunnel endpoints are calculated or how tunnel endpoints are learned in the systems. So when you look at this example here of one single over-the-top fabric, you have the leaf seeing 2 VTAPs of fabric 1. That's the NVE peers. Everyone heard of the NVE peers? Yes, somewhere, yeah. 2 local, and then 3 which are remote. In that left scenario, there is no separation of these fabrics, so everyone can talk to everyone. I'll ask again, who is good in math? Who remembers n squared minus 1? So if every VTAP needs to talk to every VTAP, how many tunnels you have actually in that left scenario? I can't remember, but there's somewhere slides which say how much it is. Anyway, if I can reduce the tunnel neighborship, the tunnel proliferation, I can exponentially scale, which is the multiplication of these fabrics which we do. Now, I gave you the number of 256 within a fabric and 128 times. I can actually do more, but that's what we validated so far. Our intra-fabric scale or single fabric scale is somewhere at 1,053 VTAPs, which we can have as a neighbor. That's quite a large number when you can multiply that. but obviously you need to have some resources left for the border gateway, so you can have internal tunnels and external tunnels as described here. So we limit you to 256 today. Subsequently, you might see 512. What is 512 times 128? Double the number of what you just saw, so 64K, whatever else. Big numbers, big scale. Anyone has a need for more than this? Sorry, for more than this? More than 32,000? Anyone wants to go bigger? Smaller? Maybe we can do smaller too. Anyway, of course, other use case was data center interconnect. Data center interconnect came naturally. You have multiple data center. Anyone has only one? Probably not. So you want to interconnect it in a certain way. You want to have it in a seamless way. You don't want to learn 500 different technologies in order to make it work. It just should work. So we put it as part of the fabric by adding multi-site there. And this here, actually, you can do within a geographic location, meaning metro, less than 100 clicks, or you can do that across the continent, given there are two protocols which are running there. One is BGP. What's BGP based on? TCP, very reliable, so I can do an easy session around latency without any issue. What's the other protocol? It's VXLAN. VXLAN is IP UDP. It doesn't care on session state. I send it and I forget it. There was a question somewhere back there. I hope I can hear you. I cannot promise. Ha! Good question. These VTAP numbers here, do they change if you have VPC or not? So yes, these are VTAP numbers. So their VPC counts. VPC is 3 VTAPs. If you do advertised PIP, it's 1 VTAP if you keep it consistent. But you heard me saying that we extended somewhere in the 1053 space. The reason why we did this, we want to go away from how many VTAPs you really need to count down to how many switches you can connect hosts to. And when you do 1053 and divide it by 3, you get somewhere north of 300 a VPC domain you can actually create in a single fabric these days. So we're moving forward by changing numbers a little bit to make it easier for you to count. Does that help? Cool. All right, DCI we nailed. Other use case is nothing is greenfield. Let's be honest, I would love to run into a company and say, hey, let's build everything new today, forget all the rest. So nothing is greenfield, and somebody decided to use it legacy networks. Well, it's a history you have, a legacy you get as you go in there. So all these VPC-based or fabric path or whatever you name them, they're just the legacy of whoever was there before or of yourself, which is good because your kits are also a legacy, which are great. So these are your kits, and you want to integrate your older kits with your younger kits. Makes sense? They should play to each other somehow. So we want to integrate these legacy networks with the more modern networks. We built a function, we built a border gateway that actually connects to an Ethernet network. So we translate from Ethernet to VXLAN EVPN. We keep the default gateway on the VXLAN EVPN side. It's just on your older kits side, on the legacy side, and be able to extend all these networks into more modern network, the VXLAN EVPN network at that case, and facilitate host mobility left and right. Now, just with this, I can probably give you hundreds of other use cases that are related to that. Co-locations, edge locations. I only need 2 switches. All of this I can go and integrate into a VXLAN EVPN network with this approach. So you have a consistent architecture. Doesn't matter if you have a VXLAN EVPN network with VTAPs, meaning the servers are connected to your VTAPs, or you just have a pair of VPC border gateways and underneath a whole Ethernet cloud and have fun with that. Both will work, both can integrate. Last but not least, it's the age of the cloud, or the years of the cloud. What are we doing with the public cloud? Remember, public cloud are layer 3 networks, always. Have you seen layer 2 in the public cloud? No, I'm not talking about that one cloud thing from some specific vendor. I'm talking about general. Clouds are routed networks. Your compute instances have an IP address in a routing table. That's how things in the cloud work. Now I have EVPN, which is a layer 2 extension, which I don't want to use. Here I cannot use, but what I can do is, if I have in the public cloud a representation similar to multiple VRFs, think of tenants, bringing them in, I can multiplex them over VXLAN EVPN, layer 3 only, into my on-prem data center, and I can terminate that directly on the border gateways itself. So I don't have to build a specific infrastructure to just onboard or on-ramp or off-ramp the public cloud in there. So here, if you find a public cloud provider that does VXLAN EVPN, you can do natively. Otherwise, there is a virtual router we have available. I think it's called the Catalyst 8000 Virtual. You can plant it up there. You can do a VXLAN EVPN tunnel up there, and you're good to go. You guys are good with the use cases? Everyone good? You all good? We're done. No, we're not. Let's go a little bit into the deeper look. I promised I'd give you some more insights on what we're doing under the hood and some packet forwarding stuff. I promise I will not rush through the packet forwarding. So let's look first, where can we put these border gateways on? Border gateways is the essence of multi-site. That's the functional component which needs to be special. All the rest can be whatever VTAPs you have. I'm not saying from whatever vendor you have, but from if the vendors comply with the 9135, 9136, we're good. These are all the hardware platforms we support multi-site on. Meaning, these are the platforms that have to be that border gateway function. So look at this. The EX platform is probably around 8 years old, and you can do it. Every platform of the Nexus 9000 is capable of doing the multi-site border gateway function. And it's able to do it since the software release of 703 i7.1, which was somewhere in September-ish of 2017. So you don't have to find the latest hardware, and you don't have to find the latest and bleeding edge software release. You can actually probably already do it what you're running today, which is good. So you can even try in the lab, potentially. By the way, CML support is there. So you can simulate that in a virtual environment in your lab without even having a single hardware. Now, there's one platform which is not yet here, not yet on the list. That is the Cisco Nexus 9800, but that's just a matter of time when we are getting there. But yeah, it's pretty much every modular and fixed platform you could think of when it comes to the Nexus 9000. How much scale do I get out of these different boxes here? Quite a bit. So the 128 side is independent of the scale or independent of the type of hardware. It's 128 side with EX the same way as with FX or with others. The number of border gateway, the maximum is currently 6. It's a soft limit. You could theoretically go higher. We just haven't validated it. The amount of number of VTAPs within a site is 256. That's the current number. That's what we validated based on 10.2x. 10.3 is the same, I think. 10.4 is the same. But that's what we validated so far. You will see different numbers coming as we go to new release, as we do more testing, you will see more. Then the other piece is how many VLANs I can do, or layer 2 VNIs if you want so, and how many layer 3 VNIs or VRFs I can do. We did recently changes, again, that's in 10.2x, where you don't need an SVI and a VLAN anymore for the VRF instance. You guys remember VRF context? You had to do a VLAN, SVI mapping, and all of this. That's gone. Not needed anymore. Layer 3 VNI is just a VNI. You don't have to burn a VLAN for it, which brought us to the limit of you can use every VLAN available on the box, meaning the 4K-ish minus the reserved ones, to build layer 2 VNIs. And for each of these segments, you can put an SVI on top and use the default gateway there. Cool. So that gives us approximately 4,000, or conservatively saying 3,900. VRFs, you can do 2,000 VRFs on all of these boxes. And you can store about 92,000 MAC addresses on a border gateway. Anyone has more than 92,000 MAC addresses in a network? Thank you. You can tell me. I'm not shy. On the routing side, as you see here in the earlier platforms, we only were half as scalable. That's why FX2 is FX divided by 2, because when you look at the FX numbers, we're going into the 1 million of IPv4 objects and 500,000 or north of 500,000 of IPv6 objects. What does that mean? Remember when I was talking about MAC and IP bindings in EVPN? So we have host routes, /32/128s. How many host routes you have in your network? It's the amount of endpoints you have in the network, which means the amount of routes you probably potentially need, which is in the 1 million or 500,000 scale, depending on which platform you select. So and that's why we're always, when we go through discussions about what is my border gateway box I should use, is well, it depends. It depends on how many routes you need to store up there, meaning how big your fabric needs to be and how big your remote fabrics needs to be. What we found out so far, nobody busted these numbers yet, or I don't know of it, so we'll see. The further piece is the border gateway function, and I mentioned the border gateway function is the critical device. It's actually this device here, which is front-ending a fabric and interconnecting the two fabrics together. So you have a border gateway in Fabric 1, you have a border gateway in Fabric 2. Fabric 1 is one AS, Fabric 2 is another AS. Remember what I was talking about, the BGP next hop behavior? Yes? You will see more of that in a bit from now. So we do tunnel stitching, meaning whenever I want to leave a fabric, I terminate at the border gateway, I create a new tunnel, terminate at the other border gateway, create a new tunnel. This tunnel creation and reorigination happens at line rate. It happens on ingress and doesn't have any recirculation. Is it slower than any other tunnels? No. Does it use more resources than any other tunnels? No. It is the same way as it would be a leaf. It just goes through the box by terminating and re-encapsulating. We want to keep these fabrics separate, and we want to keep the transit separate. That's why we're building individual underlay domains. You see there, Fabric 1 underlay, Fabric 2 underlay in green and orange. The IP addresses are the loopback IP addresses of our VTEPs. You will not see in green a route of orange. You will not see an orange route in green. This is underlay. This is not the host sitting in the overlay. These are the VTEP addresses itself. So what I do is I separate these two fabrics hardly by building literally two different networks. The only thing that needs to communicate to each other are the border gateways, and for that I have IP addresses on the border gateways. Here I have 111213, 21212223. They are talking to each other. So how much IP addresses do I need to interconnect to VXLAN EVPN fabrics? 1 per border gateway plus the virtual IP address per set. Or 3 in that case. So I can separate things nicely. I don't have to bleed things over nicely. They're separated in its existence. Can I do multiple ASs? Yes, you can do multiple AS within a site. I don't care. As long as you're following the concept of separating these fabrics, underlay routing tables, and keep these domains clean as I show here, you can do multi-site with whatever routing protocol you want to do. I don't care. I can tell you what the simplest way is, but that's not the conversation here. So a couple of more things related to border gateway. I was talking like probably for the last half an hour or so about border gateways. What the heck are these border gateways? This is our termination point. These are our borders. These are these Bs, these dark blue ones, these re-encapsulation boxes. You got that, right? We're done with this. Next. We have two modes of them. We have an Anycast border gateway, or what we call a shared nothing. So it's individual boxes. I represent it here in 4 on the left-hand side. And they are one mode we are supporting since day one. They can sit on a leaf, dedicated, or they can sit on a spine, co-located with the spine. The other border gateway mode we have is what we call the VPC border gateway. So it's not just a border gateway. I also have the ability to make them look like one. Remember the legacy connectivity I was talking about? Having an Ethernet network or having host connected to. So these are the two different modes of border gateways we have. A little bit more about the Anycast border gateway. It has a maximum of 6 in a cluster, which means you can have 6 nodes doing exactly the same. Is that enough? We started with 4. Somebody asked for 6. We just added 2 to it. Now it's putting on a slide. We can go 8, 16, 32. I think 32 or 64 is somewhere where the ECMP resources come a little bit into the gap. But we're doing this since 703i71, meaning since the first release on the leaf, and then subsequently we added to the spine, so you can co-locate it with the spine, so you don't have to have a box which is border gateway, a box that does spine. You can merge them together. The border gateways itself, as said, each of them has an individual IP address, what we call the PIP, primary IP address. And all 4 of them or 6 of them share a common virtual IP address, which is where the tunnels are being built towards to. So from a VXLAN perspective, it looks like one single node. So what happens if one node disappears and there are 4 remaining or 3 remaining? Nobody even figured, because you just go to the remaining 3. So that's the beauty of these Anycast approaches in there. Another thing to say is this is probably the fastest converging system you see, because it doesn't create any remote changes, meaning if a node fails, border gateway fails, nobody remotely actually knows of this because it's hidden behind that virtual IP address. There is literally no network-wide change, which means we're just rerouting the traffic going to that respective border gateway or one of the 3 remaining ones who still hosts that IP address there. Good with that? You guys can ask questions. I might answer them. No, I'm just kidding. The other one is the VPC border gateway came later. VPC border gateway, our focus was related to connecting Ethernet devices and doing also migrations. Or if you have a very small fabric, you say, I have 4 VTAPs, I want to do a border, I want a VPC up there, I want to connect my firewall there and also put a couple of hosts. That's where the VPC border gateway comes in there, and it's since 9.21. Now that's also years back, so it's not just yesterday when we added there. And you can see it allows you to dual attach directly devices to it. When to use what? Your choice. First, if my Italian friend Max would be here, he would say, always go Anycast border gateway. He is right, because it's the simplest way of doing things. You give a dedicated function to a dedicated system for creating that data center interconnect or that inter-tunnel stitching if you want so. So when should I use VPC border gateway? Why the heck have you guys even done it? So the answer is we want to make sure that classic Ethernet or fabric path networks can be integrated. If you have a firewall that needs to be connected, can be attached. So we want to give you an option. Smaller networks as an example, or these migration integration cases. When I go to the next slide, you see why they look slightly different from an implementation perspective. Next slide. Anycast border gateway, pretty clean. There is no link in between them. They talk to the route reflector inside of the fabric. They talk to the other border gateways outside of the fabric, or an intermediate router or so. Each of them has a personal identity, the PIP, the primary IP address. How do I talk to that BGP router over there? And then all together share a data plane IP address, the virtual IP address, the multi-site VIP, as you see in red there. What else is speaking between the 4 border gateways in that case? It's only one protocol. It's BGP EVPN. Nothing else. That's our sync protocol. And you know from when I said, hey, do it around the world, it's a very resilient protocol. It's a very lean protocol from sharing things in between. You share what you need to share. If somebody doesn't care, you don't share. But sharing is caring. The other one is the VPC border gateway. The VPC border gateway we built, let's call it upside down. We said, how can we connect hosts and firewalls or load balancers also to a multi-site border gateway function? So we took the VPC complex with the individual primary IP addresses, with the VPC virtual IP address, and we added multi-site border gateway function on top of it. How does it operate? It operates exactly like a VPC leaf, but it can stitch tunnels as well, the same way as the Anycast border gateway does. The VPC border gateway has a natural link in between the nodes. Now, that natural link is actually something really good in this case, because I can use it as an underlay routing link. So my failure scenarios I can accommodate are actually a multitude, meaning 2 ways, 3 ways, even 4 ways failure on 1 or 2 devices, versus in the shared nothing. In the shared nothing or in the Anycast border gateway, if one node has reached the threshold of a failure, we remove it from the equation. In the VPC border gateway, if a certain failure happens, another failure needs to happen, another failure needs to happen, and another failure needs to happen before we actually take the border gateway out. Why? Because we can still reroute traffic. We can reroute traffic over this little link here, meaning if there is an outage on the fabric side, I can go over that link. If there is an outage on the DCI side, I can use that intermediate link. I can even accommodate zigzag failures where on one border gateway, all the internal links are gone, and the other one, all the external links. So I just go in, cross, down. Do you want that? I'll give you the options. You can do it. It's there. It's a natural function of the VPC border gateway. And it's written in slides how it works. So it's not just, it actually works, really. So these are the different border gateway functions, different border gateway types, the different modes, what is the speciality around them, and so on. Did that help? You guys just want to see packet walks. I know, I know. There's a question over there. I'll try to hear you, I promise. Ha! Okay, I think I got your question. You're using NDFC Nexus Dashboard Fabric Controller. For multi-site, you don't see the Anycast border gateway. Well, we just call it border gateway in there. We call it border gateway or border gateway and spine. That's the role definition in there, but it is there, I promise you. I promise you. It's just the role of the switch needs to be set. Check for border gateway, you will find it. I'm sure about that. I wrote the code. No, I'm kidding. I cannot write code. I can only do slides. I promise, I cannot write code. I can copy-paste code. But let's go into control and data plane functions. We spoke about the boxes, the roles, but now what is the procedure that is actually in there? And again, I'll go back to this little overview here because that's literally what we do. We have Fabric 1, Fabric 2, we have border gateways, we have the interconnect. Remember, these are the border gateways. This is an EVPN session in between. This is my leaf on the other side, and we do tunnel stitching, as you see with this denotation there of layer 2 and layer 3. How many sites do I interconnect? I don't care. The importance is you do tunnel termination and tunnel reorigination. It's not tunnel in tunnel. Tunnel comes in, stops, new tunnel, stops, new tunnel. Very simple. We're not double stacking or anything like that. Because we're reoriginating these tunnels and we're using BGP with different ASs for the different sites, we have an automatic loop protection in place, which BGP gives us, which is the AS path check. Anyone knows how to disable that? Good luck. It still works, by the way. But again, we put protection in there. If you disable it, there's still protection in there. Make sure that nothing breaks. But all of these natural behavior of BGP, which matured over decades, is helping us here to create a rock-solid infrastructure in that DCI space. The other thing is, how do I deploy things? What protocols do I use? What is a separate AS? What is the same AS? So there are two modes which we're calling. There's one, the IEI, and the other one is the EE. Now it gets complicated. What does the I stand for? I use an IGP in the underlay within the fabric, and IBGP for EVPN. So this here, IGP plus IBGP. single AS. Very simple. Route reflector, VPN address family, that's how things were built. I do the same thing over here. Let's say I use OSPF. Don't kill me, we can do ISIs too, if you want. So let's say we use OSPF here and OSPF there. All the loopback addresses of the underlay, are they in BGP? No, I just said they're in OSPF, right? They're in the IGP, so they're not bleeding. Now in between here, I use eBGP as an underlay protocol because I want to use the next hop behavior. Does an IGP protocol automatically export routes or redistribute routes into eBGP? No. So guess what? You remember these underlay tables I showed you for green and orange and that different cloud in the middle? I have natural segmentation. Natural because I don't redistribute between these protocols. I don't redistribute between my intra-data center fabric and my inter-data center fabric. Sounds somehow like inter-AS option documentation. I don't know who wrote that. He must be a smart guy. It wasn't me. So we do IBGP, IGP, IBGP within. We do eBGP for underlay and overlay in between, and we do again IGP, IBGP on the right. Easy. The other one is EEE. eBGP within for underlay and overlay, eBGP in between for underlay, overlay, eBGP within for underlay and overlay. What's the disadvantage? What happens with all the loopbacks if I use my underlay in the same routing protocol? It's a natural advertisement which happens from the underlay here into the underlay here, and then ultimately in the underlay over there. Can I fix that? Yes, you can do filters. It's your choice. It works. I can get it working. We test it. It works. It's just a little bit more effort. Did I say something wrong? Wow. The eBGP police is coming. Joke aside. So both works. One is simpler. How protocols were built, inter-AS option B, you only have eBGP between two ASs, meaning two domains. The other one is what other people believe is the right way to do, is EEE. And if you want to learn more about it and what the differences are, I have a little link down there to a blog, which writes in 450,000 words, why one versus the other you choose. If the link doesn't work, put it into the Teams room. I'll send you the later link, and we'll make sure that it works. How do I interconnect these two fabrics together? Well, one is I need to have a transit protocol in between the border gateways where I can advertise the loopbacks left and right. That is just a routing protocol. I use eBGP in between because my border gateway in Fabric 1 has an AS and my border gateway in Fabric 2 has an AS, so it naturally becomes eBGP in between. I can do an EVPN overlay session, meaning an EVPN peering either directly in between them, or I can use a route server in the middle. What is a route server? It's an eBGP route reflector. When do I use one versus the other? If I have two sites, and I have two border gateways in each site, how many BGP sessions do I need in order to do a full mesh between all of them? Each needs two, right? So 2 sessions needs to be up from an overlay, from an EVPN overlay perspective. I'm not talking about the underlay, who cares about that? So it's 2 top. If I have 2 sites and 6 border gateways, how many sessions each have? If I have 5 sites and 2 border gateways, it gets a multiplication of a lot of peering sessions. If I want to ease my operational part, I'll put, oops, I'm sorry, wrong click. I put a route server in the middle and just, well, 1, 2 for redundancy. I use a route server and let my border gateways just peer to the route server and let the route server do the reflection work it was supposed to do. When do you need what? I don't care. I give you somewhere north of 2,000 BGP sessions out of each border gateway, so you can do full mesh whenever you like. But it is a full mesh. Every border gateway talks to every other border gateway with EVPN. Just remember that. It might still work if one is missing, it might still work if another one is missing. At a certain point, your resiliency fails, and that's when things go crazy, meaning you have black holing. We don't want black holing. That's why I show you an alternative by using the route server functionality there. Any questions to this? No? You guys are good? Packet walks, that's why you were here, or that's why you are here. I have a network device up there. Anyone raise his hand? Sorry, I didn't want to ignore you. Okay, you're all good. So we have a network device up there. I call it the dating network, where control and data plane meet. It's up there. What is that network device? In our conversation, it will become a border gateway, but in order to become a border gateway, what do we need? In addition, we need something like a fabric, more leaves, meaning tunnels coming from a leaf going to the border gateway, and they want to go somewhere else, potentially something which will show up here on the right-hand side eventually. The network device wants to have a VTAP on top. Isn't it a VTAP? Well, there's a lot of discussion around that. The VTAP is a function on top of a network device. The network device is called a network virtualization edge when it hosts a VTAP. So the VTAP is more or less a loopback interface if you want. So I just use it interchangeably because I'm getting tired to just repeat things. Oh, a VTAP is hosted on top of an edge device. We'll leave it on the side. So network virtualization edge, it's still a network device. It's a router. It's a switch, whatever. It's a packet forwarder in that sense, which sits there. And on top of that packet forwarder, there is that VTAP hosted on top of it. As I mentioned, this is now just a VTAP, a network edge. Let's make it a border gateway. All right. We actually added a remote fabric with another border gateway there. So now we have border gateway to border gateway communication, which means now we have two sides, and now it becomes a border gateway at that point, where the function of understanding of local VTAP, remote VTAPs, and that tunnel stitching comes in. If Fabric 2 has 256 VTAPs over here, if Fabric 2 has 256 VTAPs, how many VTAPs will this border gateway see? The one in green. None of the ones within the orange fabric. 0. We'll only see the border gateway in front of orange, which is how many devices? 2, 4, 6, max of 6, right? People could call it network abstraction, but I hate the term of translation or masquerading or anything, because the only thing what it does, it's just hiding the infrastructure part, what is underneath, as everything over the top, meaning all hosts in your VXLAN tunnels, are still visible. It's just the infrastructure which we're moving away, which we're hiding away. So we're creating this tunnel stitching at this point here. This border gateway has tables. You remember when I was talking about tables of host routes, MACs, VLANs, VRFs, and so on and so forth? So we have tables. That means we need to store something in these tables. We need to fill these tables. And if we want to fill tables in EVPN, there are two things which need to happen. One is I need control plane. Need a control plane, which sends me information. The second one is I need to have VRF definition. EVPN has two different types of VRFs. One is an IP VRF, the other one is a MAC VRF. MAC VRFs are stored. What is stored in a MAC VRF? MAC addresses. What's stored in an IP VRF? IP addresses. Simple. Both of these VRFs have different route targets. The route targets define what is being installed into that VRF, and respectively in the hardware table you see here empty at this point. Where do these route targets sit? Well, one is in your configuration. The second one, it's in the routing update. So let's see what happens if you get a routing update. This is an EVPN NLRI. It's a route type 5. So this is an IP prefix route. We see a prefix of 10.10.10/24. We see a label. The label is equivalent to the VNI. You remember when I said a lot of documents in EVPN are MPLS related? That's why that field is called the label field, but it's the VNI in our case. You see the route target? This is the route target for your IPVRF. Why is it for the IPVRF? Because it's an IP route update. Kind of makes sense. Do we have a MAC route target here? No, because we don't install anything in a MAC table. We have a next hop. Who is the next hop? The remote border gateway. So it's not the originator, not the leaf who sends it, it's the other border gateway that sends me that next hop. And again, remember when I said from the very beginning, BGP next hop behavior becomes very, very crucial in what we're doing here. The last one is the router MAC. I tend to explain it a little bit more when I do my VXLAN talks. VXLAN is a layer 2 encapsulation. That means it always has a MAC header, inner MAC header. When you do routing in Ethernet, what is in the MAC header of Ethernet? Source IP interface, destination IP interface, right? That's how you do MAC IP mapping. Correct? Yes? So same thing here. That's what we use inside the tunnel from the source VTAP to the remote VTAP, and we call that the router MAC. And the router MAC is there, so I don't have to ARP over that tunnel, but get actually the programmable IP to MAC binding for next hop to router MAC already in the control plane, which makes that tunnel even more resilient, meaning no bump traffic in that case for layer 3 function. All right, I mentioned we have route targets, we have a VRF definition, so we do a VRF import. Route comes in, VRF import, we store it. Hey, wrong click. We store it in the routing table, RIP, software, FIP, hardware, and we store it with the prefix, the mask, the next hop, and to what VRF it belongs. Import operation. Now I want to send that route further to everyone else. I want to send it to who? To that leaf, so I need to do an export. Some people call it redistribute, some people call it advertise. It's correctly would be an export. And what do we use for an export? Again, a route target. We assign a route target to that export, the export route target. We're sending that down. We're sending it, in this case, here to the leaf. And we send it modified with at least one thing being modified, which is what? The next hop. So I told you, it's all about next hop. Now, given the next hop IP address is different, what is also changing? The inter-tunnel MAC address, so the router MAC address in that case. I signal this down to my leaf, and respectively, my leaf would also do an import there. But here, we're staying on the border gateways table, which right now has a 10.10.10.0 with a /24, 10.10.0.2.1 VRFA to the remote Fabric 2 border gateway. Good? Okay. You're good. Really? Clear for everyone? That's the time for question. Now layer 2 comes in. Layer 2 is heck of complicated. What's again the router MAC for? No, I'm just kidding. Just kidding. So let's say we want to do more extensions. We're not just want to do layer 3 extensions, or layer 3 VPN equivalent, or IP routing. We want to stretch subnets. We want to do something in the same subnet or something in a different subnet. Let's start here. There are different. I clicked. There's a different route type in EVPN. Route type 2. MAC IP route. MAC mandatory, IP optional. Can it be MAC only? Yes, absolutely, it can be MAC only. Is it always MAC IP? No. It's actually the case that in our implementation, we are sending 2 routes. One is MAC only, and one is MAC plus IP. Why? Have you ever heard of non-IP protocols? Will I ever receive a MAC IP route in a non-IP protocol? No. But I still want to make sure I learn the MAC address in a proper communication. Or do you guys like unknown unicast flooding? We don't. We want to converge the network eventually, so we have these routes there. So you see the MAC and the MAC length /48 is, I think, what somebody came up with is the MAC address length. And then you see the IP address with the IP length of a /32. What would be the length of an IPv6 address? 128, so this could equally be an IPv6 host. If you have multiple hosts, multiple IP address, dual stack, or so on, you have multiple MAC route with different IP addresses. The good thing is, most of these routes are just stored in CPU and memory. Cheap. TCAM or hardware table, expensive. So very often, they're just being passed through. Meaning, if you don't create the VRF, what is going to happen? I'll just don't do anything with it. Comes in, look at it, oh, not for me, no VRF import, I send it forward. But if there is a route target 1 or route target 2 defined on my box locally, I will import it. Route target 1 is for bridging. Route target 2 is for routing. Remember the IP verb in the IP prefix? We only had one route target. Why? Because there is only one VRF definition. Here in the route type 2s, you actually have two VRF definitions stored. One for MAC and one for IP, so you have two different route targets. You also have two different labels. One for the bridging option and one for the routing option. So when I want to do bridge, same subnet forwarding, I use a different VNI than when I want to do route. Why? Because these are actually different tunnels. Layer 2 tunnel versus a layer 3 tunnel. A tunnel that preserves the MAC address end-to-end, a tunnel that changes the MAC address hop by hop. Well, guess what? I just explained to you how routing works. You guys already know that, so why am I even talking here? Next hop again is different, and you see down here we have again the router MAC. Why? Because we said we have two different tunnels, L2 tunnel, L3 tunnel, so I want to make sure we have all the information to create them. So we import the information, MAC address, and next hop into the MAC table. Now I say VLAN 10. How did I figure out VLAN 10? There was a VNI of 30,001, and now I say VLAN 10. It's the configuration. You are defining for what VNI you want to use what VLAN. Now, given this border gateway doesn't have any layer 2 ports connected, at least in this idea I have here, does the VLAN really matter at that point? And the answer is no. You just need to address a bridge domain where you can import it in. VRF, slightly similar. How do I know that VRF-A is mapped to VNI 50,000? VRF context, VRF-A, VNI 50,000. Enter. You configured it. Is the VNI relevant for the import? It's not. The route target is relevant for the import. This is a little bit of multi-protocol BGP education here. Sorry for that I'm doing these turns, but I want to make sure that everyone can follow of what is happening here. So again, as said, we do an import of the MAC verb and ultimately into the MAC table. We do an import in the IP verb, respectively in the IP table, and the IP tables, which is FIP or RIP, TChem, whatever you want to call it there, and it will be hosted as a /32 next hop, respectively to the remote border gateway there. What would happen next? We have to do an export if we want to send it to somebody else. So the export in this case is I send it to my route reflector within Fabric, what is it? Fabric Green or Fabric 1. I don't draw the route reflector. I don't have enough real estate here, even as these big things are there, bless you. So I send it to leaf, or L, and L receives a BGP update, which looks pretty much the same as the route type 2 I just received from the remote fabric. With what is different? There might be a couple of more things that are different. So definitely we have router MAC and next hop, which changed. Look at this, the route target changed. How can that be? I use 65002 for import, and now you do 65001. What we are doing is we're re-advertising the route, so you do a reorigination. When you reoriginate, whatever the export route target is you've configured on the border gateway will be the export route target you send out. Can it be 65002? Absolutely. I just put the same import and export. Can it be different? Absolutely. Does it matter if it's different? No. As long as I know what it means, I'm fine. I omitted a couple of things which I want to make sure that I call them out. In EVPN, there is something which we call auto route target. You guys heard about it? Automated route target? The automated route target is autonomous system number, column, VNI. So my route target coming from over here, remember it was 65002, will be 65002, 30,001, 50,001. And then it reached this guy here, or this lead here. In what AS was this one? 65001. 65002, 65001, right? What did I say is the import route target? 65002. If I do route target auto, what would be the automated import route target? 65001. So how is that import happening here? There is a magic knob. You can actually tell on this border gateway here, rewrite the AS portion of the route target to the AS number the neighbor border gateway has. Okay? So when I get a 65002 50,000, and I'm appearing to 65002 from myself, I can allow to do that portion rewritten. Why are we doing this? So you don't have to configure anything. Because when you create an IPVRF or a MAC VRF, route distinguisher and route targets don't need to be configured. We set them to auto in the back. As a result of it, the configuration you use for a VXLAN EVPN configuration or setup goes actually down from approximately 30 or 35 lines per VLAN VRF combination to something less than 10 commands. You can obviously configure every single line if you want. You remember how many layer 2 segments we can do? 3,900. Do you remember how many VRFs we have? 2,000. Combination of about 6,000. What sounds better? Less than 10 lines or somewhere north of 30 lines? I know which one I like, but then you need to know some of these tricks here, which we added. By the way, this is well documented in how it works, how it proceeds. Another thing I not forgot, but I haven't put on slide is, anyone works with 4-byte AS numbers? You remember? 2-byte is what you see here. Where does 2-byte end? Somewhere in the 65, 5, 34-ish. And then 4-byte is obviously bigger. The route target has a 2-byte, 4-byte fixed allocation. Route target is 8 bytes. 2 go away from the type. You have 2 in the front, and you have 4 in the back. So how would I represent a 4-byte AS number? Oh, the smart guy would say, let me just move the 4 bytes from the back to the front, and I have 4 bytes in the front. That works great, but your VNIs is a 3-byte field. So potentially you're overloading your service identifier or your VNI or your VRFs at a point, which might become a little bit difficult. So keep these 4 bytes on the back for the service identifier or the VNI, and represent the 4-byte AS number in a 2-byte. How can I do this? There is a standardized nomenclature for this. It's called AS trans, which uses every 4-byte AS number and transposes it in a 2-byte, which is 1, 2, 3, 4, 5, 6. You guys are still able to follow? I know I haven't put it on the slide, but I want to make sure that you guys hear this. So if this 4-byte AS number is different than this 4-byte AS number, the route targets are the same. 4-byte AS numbers for the win. Just a little side note on that point. Was there a question? I saw a hand at a point. No? Okay, good. All right, let's see what we do when we want to do forwarding. Color is red. Red represents what? Routing. Blue represents bridging. So we do routing here. We want to route from 192.168.0.12 to 192.168.1.12. So 2 different subnets, natural routing operation. And we have, where's the border gateway again? We have here the tables from the border gateway itself. Now, I put these tables there to give you a little bit of a hint what happens within the fabric and what happens when you go outside of the fabric, meaning after the border gateway. So let's look here. Source IP address 1111. Looks like next hop of 192.168.0.12, so this is host A. So that's what the border gateway sees internal. This is the internal VTEP IP address as the source address. The destination is 10.0.1.1. 10.0.1.1 is this border gateway's virtual IP address, meaning that VTEP address, that Anycast VTEP address, if you want so. VNI 50,000, how do I know? VRFA is mapped to VNI 50,000, and respectively the route targets which are representing this in the control plane. This is data plane, so there is no route target. You remember my router MAC explanation of I need a source MAC and a destination MAC for the inner routing tunnel. You see this here, and this is again learned and stored based on the NVE peer information driven through the control plane, so we're not doing ARP resolution in the routing tunnel. It's a true L3 tunnel at that point. And then you see source IP address of 192.168.0.12, 192.168.1.12. Host A sends a packet, realizes it's a remote subnet. If it's a remote subnet, what are we doing? We're hitting the default gateway. Destination MAC becomes the gateway MAC address, the default gateway MAC address in here. And that's why we're driving here a routing lookup telling me that if you want to know of this destination of 112, you need to go to the border gateway because it sits outside of the fabric. Could it be a default route? Yes, it could also hit a default route, but I'll just go with the specific host routes in this case. So I'll send this to the border gateway. The border gateway removes all the VXLAN headers. Remember what we did with import? So we terminate the tunnel and recreate that tunnel. Source IP address 10.0.1.1. Who is 10.0.1.1? Is this body here. Who is 10.0.2.1? And how do we know that we need to send it? Because our routing table tells us 192.168.1.12 is behind 10.0.2.1, which is border gateway remote for Fabric 2. VNI is 50,000 because I choose so. Could be a different VNI. Yes, we can do VNI translation or VNI stitching. How do we get the inner source MAC and the inner destination MAC? NVE peer tables based on the routes we previously got in EVPN. What doesn't change? The source IP address and the destination IP address for the respective host-to-host communication that exists. Good? Can we do the same thing with blue? Exactly the same thing happens, so we can close here and I'll see you guys later. No, we'll go through. Again, host A wants to send to a host in the remote side. This time, we want to have a communication from MAC address 100A to MAC address 100B, and the hosts sit in the same subnet, 192.168.1.5, 192.168.1.12. Who decides that I need to present the MAC address in the inner header, which is the host MAC address? Who decides? It's the leaf down here. So host looks at it, says, hey, I know who that 192.168.1.12 is because it's in the same subnet as me, which is 1.5. Somehow I have an ARP resolution happening at a point in time, so I know MAC IP binding in the host, so I'm going to send it out. What's my destination MAC? When it hits the switch, the destination MAC is the remote host's MAC address, so the router, the leaf, will look at it and say, okay, not my MAC address, I don't have to do a routing lookup. If it would be my MAC address, meaning the leaf's MAC address, I need to do what? Routing lookup. That's routing bridging definitions of how these things are going through. So we have a different VNI here. Who is it defined? On leaf, I have either a trunk port or I have an access port with a VLAN mapped to a VNI, definition of the MAC VRF if you want to call it this way. So we send it to the leaf. And we have decided 10.0.1.1 is the exit point, which is this border gateway, just because it's not local to my fabric, so we are not living in green. We need to go outside of green. As we send this to the border gateway front-ending the fabric 1 or green, there are lookups happening. And you see now that 100A is 1111, which is local, and you see 100B is remote 10.0.2.1. Who is remote? The border gateway in the other fabric. So the decision is being made on the border gateway to not drop it, but forward it. Now, trick question. What if 100B is not in the remote fabric, but right here in fabric 1? It would never end up on the border gateway. The border gateway is only involved for non-local endpoints. So it's not like, oh, let me send everything up there and he can go and figure out. No. In VXLAN, tunnel modes, EVPN, closest to the source, closest to the destination. No tromboning. No go in the middle and go back. That's why we use the distributed anycast gateways in all of the leaf switches, because we don't want to go to a central point and eventually go back. Okay, so we're hitting it. We're hitting a border gateway. Border gateway does that decapsulation, and based on the tables which we previously learned from EVPN, we're recreating the tunnel. Source IP himself, destination IP remote border gateway, VNI, whatever the VNI is of the MAC VRF configuration, MAC addresses stay, and IP addresses stay. And MAC addresses stay in the internal because it's bridging, and we are not allowed to change the MAC headers in that point. Has anyone seen a switch that does MAC address change in bridging? At that point, it's not called bridging anymore. It's becoming a routing approach or a MAC rewrite approach. Everyone good with this? Yes? No? So I'll give you a conclusion to it. We're talking about two things. One was some draft stuff, just to give you a little bit of a base. But we had two main things we went through. One is the border gateway. Hardware, software, and all the procedure. And I hope you understand that in the architecture of multi-site, what is the most critical device? It's the border gateway. Who came up with the name? I had no better idea. So we just mixed border, edge of a network, and the gateway, translating things, put it together. Anyone ever deployed an AGS or AGS Plus? AGS? Yeah, that's the old Cisco white boxes with the orange stripe on it. Thank you for being with me on this modern stuff. So AGS were what? What was the G standing for? Can you remember what the G was for? It was gateway. So that's one of the first products we did, and we're back to gateways, which we're doing in these world, transposing things between different protocols, in this case in the same. Remember, layer 2, layer 3 extension. Can we do that with multi-site? Yes. Can we do it with RFC 9014? Only layer 2. So that's where multi-site complements 9014 and adds the procedure which is in the, listen good, EVPN, IPVPN interwork draft, and move that to EVPN, which is also represented in the EVPN, IPVPN interwork draft. You guys followed? That was very complicated. No. So basically, EVPN, AVPN, IPVPN is the same procedure. That's the bottom line. So we tried to document this as part of the multi-set. If you have more questions, I hope you figured out how that WebEx app works. And otherwise, I'll take a couple of questions because I was efficient in time. Please.
Yeah, back on slide 40 something where you talked about the border gateway times.
Okay. I will not click back, but please go on. Ask a question.
There was some text regarding external connectivity.
Okay, good. Border gateways can do more than just being border gateways. I mentioned there can be spines. There can also be L3 out connectors or external connectivity, so VRF Lite subinterfaces. You can do that at the same time. The Anycast border gateway needs to have IP interfaces. No trunks, no SVIs. The VPC border gateway can have SVIs, trunks, and all of the other shebang, so choose wisely. Now, the fun thing is, I can have on my parent interface, Ethernet 1.1, VXLAN multi-site, and Ethernet 1.1.1 subinterface with .1Q with a VRF external connectivity. So I can do it on the same interface, or I can say VXLAN stays on Ethernet 1.1, and I do sub-interfaces on Ethernet 1.2 point whatever, 1, 2, 3, 4, 5. So both of it is able to be combined. Good? All right. I want to make sure that you guys don't come late for coffee, but please, if you fill out the survey, it helps me to get better, to have better jokes, change my accent and everything else. You will find a lot of NDFC-related stuff in the world of solutions, so you should actually see how border gateways are being configured. Capture the flag is cool. Has anyone done it? It's kind of little laps, and whoever is fast goes first and gets some prizes. And so have fun in the education part, and thanks for being here with me, and I'll hope to see you soon. Yep, thanks.